Consider the following. What if we want to find dy dx for x squared plus y squared equals 1? Okay, standard equation of a circle with a radius of 1. How do we get dy dx? Based on what we've done so far, you might think, okay, solve for y. That's 1 minus x, the square root of plus or minus the square root of 1 minus x squared, then take the derivative. It's a little messy. You might wonder, is there a better way? And you might wonder on top of that, can you just take the derivative straight out? And you can, using a tool that we've talked about, differentials. So here's the idea. You just start taking derivatives, and you keep track of what you took the derivative of. So the derivative of x squared is 2x, and then you put in dx, okay? Plus derivative of y squared is 2y, so you put in dy. Now the derivative of 1 is just 0, so it doesn't matter. You don't need a dy or dx, it's just 0. Okay, great, so now what? Well, the idea is you want to treat dx and dy kind of like individual variables. And so you want to get like 1 on one side and 1 on the other. So do something like this. You get 2y dy, subtract to the other side the negative 2x dx. And now to disentangle them, we just divide by the other pieces. So divide by dx to get on the left side. But then I'm going to divide by 2y to put that on the right side so I can get dy dx alone. So you end up with dy dx equals, and then you have negative 2x over 2y, the 2's cancel, so it's just negative x over y. Now what's interesting is that when you do this, it's actually common, okay, to leave it like that. It's not required to put everything in terms of, say x. You could, okay, in some cases in particular problems you might want to, but it is actually standard in implicit differentiation, which is a mixture of x's and y's together, to have your answer in terms of x's and y's. Again, the name for this technique is implicit differentiation. Nice naming, differentiation. Okay, and let's try to get a feel for it by looking at some examples. So consider the following. Okay, let's try this one. How about the natural log of x plus xy equals y squared? Okay, and for all cases, we're going to find dy dx. Okay, so how do we do that? We just start taking derivatives. Derivative of ln x is 1 over x. So I get 1 over x dx. Take the derivative of x. Now this xy is very interesting, okay? Why? Okay, it's a product, so we need to use the product rule. So when we take the derivative of x, okay, that's 1 dx. You could just think of it as dx times y. So when we do like the first derivative, it's a dx times y. And so we can write that as y dx. You can also write it as dxy. And the reason why I think that's interesting is because it says y dx, but we just took a derivative of x. So it's not always the case, kind of like in this one, you see 2x dx, we just took a derivative of x. Certainly when I see 2x dx, I think, oh, there was an x squared, okay? So that's kind of interesting. And by the product rule, we need to take the derivative of the second term. So what's the second term? Well, it's the derivative of the second term is dy times the first term, which is x. So it's x dy. And those equal, derivative of the right side is 2y dy. Okay, that's great. Now I need to get dy over dx. So how do you do that? Once again, you want to treat them like individual variables, okay? Now you see a d and a y, but just treat them like they're together. So I get my dy's on one side, my dx is on the other side. I'll send my dy's to the right since there's already one there, and I'll leave my dx's on the left. So on the left side, what I'm going to do with these two dx's is factor the dx out. Okay, that's what you want to do. So you get 1 over x plus y dx equals, and then I send my negative x dy over. And when I do that, I'm left with 2I dy minus x dy, okay? So it's 2I minus x all times dy after factoring. That's what you want to do. You want to get your dy's together, your dx's together, and put them on the same side and factor. Now it's straightforward how to get dy dx. We just bring the dx down. We'll still put it on the left, dy dx. This is going to equal, okay, what? Well, this term stays, the 1 over x plus y. It's going to be all over this other term, which is 2I minus x. Okay, so there's another example. Okay, so with implicit differentiation, you really want to get the practice in, take some time. So consider the following. Let's consider the sine of x squared y squared equals what? How about the tangent of x? And once again, we want to find dy dx. So we just start taking derivatives, okay? Now, the derivative of sine is cosine. We need to use the chain rule, okay? So you start this one with derivative of sine is cosine, so I get cosine of x squared y squared. But now I need to multiply that by the derivative of what's inside the x squared y squared. So once again, we have a product. And we sort of looked at how to do that, right? The derivative of the first term is 2x dx times y squared. So that's the same as 2x y squared dx. And then the second term, similarly, is going to be 2y dy times x squared. So it's 2y x squared times dy. And that's all going to equal, on the other side, derivative of tangent is secant squared. So it's simply secant squared of x dx. Okay, so how do I get this one together? What you want to do is, once again, get all your dy's and dx's together. The idea here, that cosine x squared y squared, you just got to multiply it through to each of the other terms. And what we'll do, we will keep the dy term on the left and send the other dx term to the right. Okay? So on the left, I'm going to have cosine x squared y squared times 2ix squared. That's all dy. And then what is this going to equal? Well, it's going to equal, you've already got the secant squared x. Okay, put that up here. Secant squared x minus, and then I've got this other cosine term. And so I've got this cosine x squared y squared 2xy squared, and that's all times dx, okay? So it's very similar to the other one, and realize it might look a little more confusing when you've got this cosine x squared y squared. If it's helpful, you can break it down into more steps. You can multiply the cosine x squared y squared out, to see it, and then get your dx terms together and your dy terms together. And then that's kind of once you're at this step, then it's simply, okay, you've got the dy, just send the dx over. So you get dy dx equals, and then what do we have? Keep your x term up. So that's where you've got the secant squared x minus cosine x squared y squared times 2xy squared, and that is all over this other term, which is cosine x squared y squared 2yx squared. Now, when it comes to trig functions, there are, generally speaking, a lot of simplifications that you can do. For me, like, I mean, maybe there's some ways to simplify this, but the fact that the secant squared is of x, and then the cosines are of a different variable, the x squared, y squared, I'm just going to leave this one and say that this is fine. Okay. Once again, you cannot cancel out the 2x, y, but those are different anyways. Okay, if they were the same, you still couldn't cancel them out because there's not one on the other side. Okay, so it's a lot to keep track of. You just have to keep track of it the best that you can. And I do want to show you another sort of way that students will sometimes do implicit differentiation that can be a little easier than the dy's and dx's. Now, here's the deal with this. When you're doing multivariable calculus, which would come, after this class, but you're going to need the dy's and dx's because there's also going to be dz's, okay? But in this particular case, you can do it a little different. So let's set up one final example, and I'll show you what it looks like. Let's go with, how about x cubed minus 2y squared equals y. Okay, so let's just start doing the derivatives, and for x's we get 3x squared. Okay, and we're not going to put dx in, okay? So this is like a shortcut technique. We take the derivative of y, that's minus 4y, but whenever you take the derivative of y, sorry that the marker's squeaky, you get y prime. Okay, so you've got to put that in there. So it's y prime. Now this y is just y prime. Okay, so reason y prime instead of dy. And in effect, like, that's the technique. It's to use y prime instead of dy and not to use dx. So it's a little easier with notation if you have a hard time with the notation, but generally speaking, the dy's and dx's are more precise and will serve you well going to higher math classes. So now you just get y prime by itself. So we send all of our y primes to one side. So you get 3x squared equals y prime minus plus 4y times y prime. Now I didn't factor it, you could, but you factor in the next step, and you get 3x squared equals, what happens when you factor out the y prime? This becomes a 1 plus 4y. Y prime. Right? The derivative of y is 1. Look, you end up with that 1 there. And so now, this tells you what the answer should be. You get y prime equals, you divide just like you did before, so you get the 3x squared over 1 plus 4y. Okay, so, honestly, when I took this, I feel like maybe even in early college, I think I did use the y prime notation because it definitely makes these a little easier. I think it's okay to implement as a shortcut, but I do encourage you to at least do a couple problems of practice with the dy, dx's. And if you're serious about math, you can still do the shortcut, but the dy, dx's are more precise. Your choice. What's really important is to find the correct answer. And the way you get that, just to recap, when you have an expression, okay, now it's not just a function, right? You've got an expression. And that expression has like a mixture of x's and y's like we see in these examples. You can just start taking derivatives, but you have to keep track of whether it's a derivative of x, I'm going to point to this one, or a derivative of y, because it's not always what you might think just by looking at it. So you take derivatives, you keep track of what's your dx's and your dy's, and you use that to get all of your dy's on one side of the equation, all of your dx's on the other side, Same thing with y primes and your non-y primes. And you solve for dy dx by dividing, or solve for y prime by dividing. That's implicit differentiation. I would use it every single time when it's not going to be easier, say, to solve these functions for y. No thank you, I'll do it this way.